Okay, we are off to chapter 12 because I think we finished chapter 4, I hope, yeah. Um, like I said the other day, we're gonna go 12, we'll go back to 5 afterwards. So in chapter 12, we're gonna talk about chemical bonding. We're gonna talk about all types of bonding, Lewis structures, how to draw them, geometry, and everything you want to know about bonding, I suppose. So let's get into it. First off, Lewis dot symbols um, are basically what we use. They're sometimes called just generically electron dot symbols. And when basically atoms come together to make bonds, what happens is those outer electrons come together to make our bonds, both types of bonding we're going to talk about, which is ionic bonding and also covalent bonding. And it's really just the valence electrons. And one of the things when we talk about valence electrons, and since they kind of move some chapters around, we don't really do 11s early again. But if we look at something, say, like sodium, it has 11 electrons. And basically, its electron configuration looks something like this: 1s2, 2s2, 2p6, and 3s1 there, which would be 6. And this is electron configuration, which we'll talk about in chapter 11 on how to write it. But basically, these first numbers here indicate the energy levels. So that's like the first energy level, which is closest to the nucleus. These twos here represents the second energy level, and this 3 here represents the third energy level, which is the furthest away from the nucleus. And it is this in terms of sodium, for example, which is its valence electron. The numbers on top is how many electrons there are. The letters are basically where the electrons are in the atom at a particular time. So in this case here, sodium would have one valence electron, and that's what it uses for bonding. It's just those valence electrons. The lower electrons, which are not used, and that's 10 of them, and that's these numbers up on top, 2, 4, and 6 more make 10. Those are what are sometimes referred to as core electrons. And core electrons are the ones that are closest to the nucleus. They are held tighter, and they're not involved in bonding because of that, because they're held really, really tightly. So it's just those outer electrons that basically will be used for bonding. So we show just the valence electrons and keep track of them using Lewis dot symbols. And a Lewis dot symbol is essentially just a symbol. So use the symbol for whatever you're drawing, and basically one dot to represent each of the valence electrons there are. There's really no big rule except that for the most part, we do not put more than 2 dots on each side. And there are 4 sides right to that, which means a grand total there of 8. And as we'll talk about in this chapter, 8 is a really important number in terms of bonding. So what's referred to as the octet rule. But we do use this sort of way of representing it. And again, those dots are just the valence electrons. Each of these elements have more electrons, which are not involved in bonding, and they're not shown here in these pictures. Most of the time, people kind of go one at a time and then kind of go back and pair up, but it really doesn't matter as long as you typically just don't go more than 2 dots per side or anything like that. So this is a Lewis dot symbols for all the representative elements. And here's the deal with valence electrons. The easiest way to figure out valence electrons is that it equals the group number. So everybody in group 1 has 1 valence electron, 2 valence electrons, 3 valence electrons, 4, 5, 6, 7, and 8 valence electrons. And that's where we get all these dots from. The one sort of notable exception is group 8 there, and that is helium. Helium actually only has 2 electrons total, and they're both valence electrons. So even though it's part of group 8, it has only 2 valence electrons, and that is because and there's only 2 total electrons total. But everybody else there in group 8 will have 8, except for, again, helium. This is also why we'll talk about shortly the reason for all bonding is for everybody to achieve like or noble gases. So this is really the reason for all bonding. Be it ionic bonding, which is between metals and nonmetals, be it covalent bonding, which is between 2 nonmetals, be it transferring electrons, sharing electrons. The whole purpose of bonding, for the most part, is for everybody to end up the same way as the noble gases in terms of their electrons. Noble gases are really, really stable. So that is really the whole purpose, pretty much, of bonding. That's also why when we do bonding, it's something people always screw up on. If we look at where hydrogen is located on the periodic table, what is the noble gas that comes right after hydrogen? It is helium, yeah. And helium has only 2 electrons. So in bonding, hydrogen should never have more than 2 electrons because it just needs to get to helium in terms of its electron configuration. So that's really important to keep in mind. But through this chapter, people always want to like triple bond hydrogen, put dots all around hydrogen. Before you know it, hydrogen has got like, 18 electrons or something like that. So hydrogen should only have 2 always, never more than 2. If you find yourself putting dots all around hydrogen, you should also put an X through it because it's probably going to be wrong. So don't do that for sure. Most of what we draw in here pretty much will deal with these elements here. We really don't draw too much that deals with transition metals. But in terms of valence electrons, they do work the same way. The number of valence electrons does equal the group number. In that case, if you remember when we were talking about the periodic table the other day, there's kind of like 2 sets of numbering, right? There's 1, 2, kind of the A numbering, and there's the B numbering, which just kind of rolls 3, 4, right? 5, 6, 7, 8, 9, 10, 11, 12, and this is like the B numbering, right? And if you ever needed to figure out valence electrons for transition metals, it equals kind of the B numbering group number there. So, whatever we got right there would have 6 valence electrons, 10 valence electrons, and so forth. But the good news, in normal sort of chemical bonding, we don't really deal too much with transition metals, so you don't have to usually worry about valence. Is it right place? Still works the same way. It's be equal to the group number, but it'd be the kind of B numbering group number where it kind of just goes straight across. Any questions on that there? So let's talk about the 2 types of bonding that we're going to talk about and see in this chapter. And this is ionic bonding and covalent bonding. And there is a difference in ionic bonding. It is typically between a metal and a nonmetal. And what happens in ionic bonding always, as we will talk about, is the metal will transfer an electrons to the nonmetal. And the result of that is you will actually form ions in this case. So the metal will become a cation, which is positive charge, as we talked about. Anion will be negatively charged. And one important sort of understanding of ionic bonding, as we'll talk about, is there's absolutely no sharing of electrons here. So we have a transfer of electrons that's happening. What holds together that bond is the electrostatic attraction between the positive ion and the negative ion. So kind of opposites attract is what holds that together. So absolutely no sharing of electrons here. Now, that is different than what happens, as we'll talk about through this chapter, when we form a covalent bond. And a covalent bond is typically between 2 nonmetals. And unlike ionic bonding, covalent bonding is all about sharing electrons. So it is all about sharing electrons. And as we will see, in some cases, the electrons are shared equally or unequal sharing of electrons. But there is some aspect of sharing happening in a covalent bond between the two atoms. So that is a major difference between those two things. The real reason for that is some things we'll talk about a little bit later on today. But it has to do with some of the periodic trends that both metals and nonmetals have. Metals have a lot of trends, as we will talk about, where it allows them to very easily give away their electrons. So they're not looking to hang on to their electrons. They're willing to give them away. They're not looking to gain any electrons either. So metals very easily will give away those electrons. And nonmetals have properties of, I really want to hold on to my electrons and I want to take other people's electrons as well. So what happens when we put together a metal and a nonmetal together, the metal's like, take my electrons, please. The nonmetal is like, cool, I'll take your electrons because I'm looking for some. And we get this transfer of electron that happens. And that's different than when we get two nonmetals together. When we get two nonmetals together, because they both have pretty much the same sort of properties, they both want to hang on to their electrons. They both want to gain electrons. Neither one of them want to give away their electrons. So the best that happens when we get two nonmetals together is they agree sort of on, all right, I'm not going to give away my electrons and you're not going to give me your electrons, but what we'll do is we'll just share. So we'll find a way to share those electrons between them. And that's because when you look at the periodic table, as we'll talk about a little bit later, upper right-hand corner of the periodic table, right, is where we find our nonmetals, and they're all located together, and they all have very, very similar trends in terms of what they want to do with those electrons. So because two nonmetals basically want to hold on to their electrons, the best that they could do is sort of share them rather than a transfer of electrons that we have with metals and nonmetals. Any questions on that there? So the general rule tells us that basically elements form cations in group 1 and 2. Basically, our nonmetals there are going to form anions, which is our negatively charged ions, our halogens, our oxygen in that area of the periodic table. So let's talk about lithium fluoride and what is happening when we put these two things together. So first off, we might want to identify what these things are. Lithium is a metal. Fluoride, which is the ion version of fluorine, is a nonmetal. So by identifying these two things, I automatically know without thinking about it, what type of bond should I have here? Metal and nonmetal should make a ionic bond. Yeah, so this should be an ionic bond that's going to happen. And really, you know that just straight up, it's a metal and a nonmetal coming together. That's always what's going to happen. You will get an ionic bond that's going to form. So when we go to the periodic table and we look at lithium, lithium is in group 1, which means it has one valence electron. So if we draw a Lewis dot symbol for it, it should look something like that. And if we write our electron configuration, it will look like 1s2, 2s, where are we at there? 1s2, 2s1. And once again, this is the valence electron that's in that picture. This one electron right here, that's on the second energy level. That is the electron that we actually see there in the picture. We're going to react that with fluorine, which is group number 7 on the periodic table, which means it has 7 valence electrons, which looks something like this. And if we write our electron configuration for this, this is going to be 1s2, 2s2, we got there 2p5. This is the 7 valence electrons right here, the 2 and the 5 that we see in the picture as they're both on the second energy level. Again, they're furthest away from the nucleus. So what's going to happen in this case when these two guys come together is the lithium, which has all the properties of, I don't really want my electron, you take it. And the fluorine pretty much has all the properties of, I'll take it. And that lithium is going to send over there its one valence electron to the fluorine. When it does that, our lithium has now lost an electron, and that is when it becomes positively charged, right? Because it lost one electron and now has more protons than electrons in this case. And our fluorine in this case will pick up that one electron that lithium sent over, and it will also gain a charge, which is a negative charge. Put a little brackets around one or both of them if you want to kind of separate them. And it is important when we draw this, because this is an ionic bond, that we do include the charges. The charges indicate that these electrons are not being shared and that we have formed ions. So what happens in terms of the electrons for each of these elements? Well, we know that lithium gave away its one valence electron, which is this, which means lithium with a +1 charge has an electron configuration of 1s2. It's basically got 2 electrons. Who on the periodic table is 2? It is helium, right? Or that is the same electron configuration as helium. Now, what happens is the fluorine actually has room for that electron right there, and it will end up with an electron configuration when it gains the electron of 1s2, 2s2, and 2p6, again putting in the electron in that one spot where it had room for it. If we count up the top numbers here, that is how many electrons the fluoride has. That is 2, 4, and 10. Who on the periodic table is number 10? Yeah, number 10 is neon, right, on the periodic table. So this becomes the same electron configuration as neon. That is what is known as being isoelectronic. These are two things that have the same electron configuration. Helium and lithium with a +1 charge has the same electron configuration. Fluoride and neon has the same electron configuration. Again, they're what is known as being isoelectronic. That right there is the basis of all bonding. Lithium, by giving away its electron, moves backwards on the periodic table to the noble gas that comes right before it. Fluorine, by gaining the electron, goes forward on the periodic table to the noble gas that comes after it. And they both end up being the same in terms of the noble gases, in terms of their electrons. And as we know, noble gases are really stable, they're chemically inert, and that is the goal here. Does lithium become helium, and does fluorine become neon in this case? They do not, because the only way they could do that is they change the number of protons, which we did not do here. So sometimes people have a misunderstanding that they become those elements. They do not become those elements because we're talking about just electrons. We're not touching anything with the protons, but they become very similar to those elements in terms of their electrons, and that makes them very, very stable. So that is the deal there. And again, sometimes people have the misunderstanding that they become those elements, but remember, if you don't change the protons, they can't change elements, right? Any questions on that there? Yeah. You do need, well, there's two ways, but the easiest way is the number of valence electrons, which are the dots in the pictures. They equal the group number. So whatever group on the periodic table that element's in is how many valence electrons that they would have.
7 electrons, like in any order, as long as they're 7.
Yeah, over here, you really can. The general rule is you shouldn't put more than 2 on a side. So as long as you don't go more than 2 on a side, you can technically put the single dot on the other side of it if you want it, or on the bottom. It really doesn't matter as long as you don't go more than 2 on the side. Yeah. Other questions? Yeah. So let's take a look at, that's what we just looked at. That's good. Let's look at the idea of what we just saw there. So once again, what is holding that together is no sharing of electrons. It is the attraction between the positively charged cation, which is in this case negatively charged anion, which is the fluoride. And again, that is what's referred to as electrostatic attraction. Opposites attract. And that is what basically holds that together. That is a super strong attractive force, one of the strongest you could have. And it does increase in terms of attraction. The larger the positive charge and negative charge, the stronger the attraction between those things. And that basically is what an ionic bond is. And that is always what's going to happen when you put a metal and non-metal together. So a lot of times people are like, how do I know it's ionic or not? That's pretty much how you know. You see a metal and a non-metal, don't even think about it. It's going to be ionic. You're going to get a transfer of electrons that's going to happen. Let's take a look at another example here. Let's say we took calcium and we took oxygen here. So basically calcium is a metal. Oxide, which is again the negative version of oxygen, is a non-metal. And once again here, that combination of those two should tell us that we got an ionic bond happening here. So once again, in terms of drawing our Lewis dot symbols here, we know calcium is group number 2 on the periodic table. So you got a couple dots happening there. And if we were to write its electron configuration, which we will learn when we get to chapter 11, but I assume in chapter 12, they assumed you did a chapter 11 before you got there. So I was kind of fill it in here. It will be 1s2, 2s2, 2p6. What we got there? Calcium, right? 3s2, 3p6, and a little 4s2 action happening there. And by the way, again, these numbers in front are the energy levels. So that's the first, these are the second, that's the third. And here we see we have some electrons on the 4th energy level, which is furthest away from the nucleus. And these are the 2 valence electrons that we see in the picture there. So these are the valence electrons. Once again, these lower guys would be considered the core electrons, not involved in bonding. So again, these Lewis symbols only show the valence electrons. They all have more electrons, but they're not involved in bonding. So it's just these guys that are pictured are the ones involved in bonding. We're going to use oxygen, which is group number 6, I think there on the periodic table. Looks something like this. So it will have 6 valence electrons, and we'll do a 1s2, 2s2, 2p4, I believe in this case. And once again, these are second energy level. So these 6 electrons, which are on top here, those are the valence electrons that we see pictured there in the picture. Again, because in the case of oxygen, those are the highest energy electrons that they have. So once again, in this case, the calcium is going to give away its electrons because it is a metal. So let me just stop right there. And if calcium only transferred 1 electron, would it be happy doing that? If you're not sure, if you look at the periodic table, which you got multiple ones in this room, but if you look at the periodic table, it loses 1 electron, which means it only backs up 1 spot, right? And it would only end up at potassium, which is not a noble gas. So that is why calcium here wants to give away not 1, but both of its electrons, so that it can really achieve what it needs to achieve. And when it does so, calcium will end up now with a +2 charge because it gave away 2 electrons. The oxygen there will pick up those 2 electrons and will sort of fill up, if you will. And once again, because it gained those 2 electrons, it now will have a negative charge. And once again here, this is an ionic bond held together by the positive charge there of the calcium and the negative charge there of the oxygen. First off, any questions on that? Yeah.
For a test. Spots.
Yeah, you would need to show kind of like how I'm showing it with the dots, the arrows, and that type of thing, something like that. Yeah.
I know sometimes they connect dots physically.
You would not be doing that in this case because this is an ionic bond. So there's no sharing of electrons. So when the dots are sort of connected, which I think I know what you're talking about, that's for covalent bonding, which we're going to talk about next. So you would definitely not want to show it in this case because that would imply that those electrons are being shared. And that's also the reason why we include the charges on the right-hand side here. And also a lot of times people put brackets around one or both of them to indicate that they're not really sharing those electrons, that they're just attracted to each other as ions and stuff like that. Yeah.
Oxygen, oxide, how many last two numbers for the valence electron and the also just the last number for the valence?
So when we look at electron configuration, we'll just dissect like this one here, 1s2, 2s2, 2p4. These very first numbers here, right? These kind of bigger numbers that come in front of the letters. These are what are referred to as the principal quantum number. And it's basically referred to as N. That is a fancy way of saying that's basically the energy level where you find these electrons. And an N value of 1 is the lowest in energy. And that is like the closest to the nucleus. And anything above that, like N equals 2, 3, 4, 5, 6, and 7, those are higher energy levels. And that's what these numbers represent. So when we look at this electron configuration, this first one means that these two electrons here are on the first energy level closest to the nucleus, and they're going to be held really, really tight because of that, and they're not going to be involved in bonding. In the case of oxygen, we do go to the second energy level, and that is as far up and away as we get in terms of oxygen. And that these are both here on the second energy level, which means we do need to include all those electrons that we find on that second energy level for oxygen, because that is the highest energy level that it achieves. And that's different than calcium. As you can see in calcium, we look at the front numbers, that's a low energy, right? First energy level. These 8 in this case are on the second energy level, right? They all have 2s. This 8 here are also on the third energy level, but now we get some electrons that are actually on the fourth energy level, which is the highest energy level in the case of calcium. And that's why we only use these 2 electrons. Yeah, so if there's like a 4p or something like that, you would include those as well if it has something like that. Yeah, so it would be technically, when you look at the electron configuration, it is the ones that have the highest kind of front number. All those electrons that go with those are the ones that are involved in bonding. The quick way to learn that is that number should equal the group number. And that's why oxygen is group 6, and that is the 6 valence electrons that it has, but calcium is group 2. And that is the 2 valence electrons that it has. Yeah. Other question about that? So speaking of that, what happens here basically is calcium will give away its 2 electrons basically there in its highest energy level, as we saw. And when calcium gets a +2 charge, it will end up with this electron configuration. And if we just count up the top numbers, right, which are the number of electrons it has, how many electrons does it have now? Just count up the top numbers. That is 2, 4, and 6 is 10, right? 2 more is 12, and 6 more is 18 electrons, right? And on the periodic table, number 18 is? It is. So by calcium giving away not one, but both of its electrons, if you look at the periodic table, it's able to back up to argon's electron configuration. And that's going to make it really happy and really stable. It achieved what is sometimes referred to as noble gas configuration by doing so. Now, the good news is oxygen here has some room for them. And that's because P, that's what's referred to as a P subshell, could hold a maximum of 6 electrons, and it only has 4 at this point. And those 2 electrons that calcium gave will actually end up right there with those other 4 electrons. And what happens with oxygen here is it will become 1s2, 2s2, 2p6, which means if we count up the top numbers there, how many electrons is that? as 10, which is neon's configuration. So here, oxygen also, by gaining those 2 electrons, if you look on the periodic table, will go forward to neon's electron configuration, making it really, really stable. So once again, that is pretty much what happens in an ionic bond. Metals will lose electrons or enough electrons to back it up on the periodic table to the noble gas that comes right before them. Non-metals will gain enough electrons to go forward on the periodic table to the noble gas that comes after them. Any questions on that? And by losing and gaining electrons, both of those things are able to achieve that noble gas configuration, which again is a very stable sort of arrangement. Any questions on that there? So what happens when we put together a couple of things here that we were talking about? Let's say we put together our calcium with its 2 electrons and its configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Once again, these being the 2 valence electrons for calcium. Now let's put it together with fluorine that we used earlier, which has 7 valence electrons here, and an electron configuration of 1s2, 2s2, 2p5, and that is the 7 valence electrons there once again for fluorine. So what happens in this case is this calcium is going to want to give away its electrons. So it's going to send over an electron here to the fluorine. Calcium, as we just talked about, is not going to be happy giving away just 1 electron, right? Because it will only move backwards 1 step to potassium, which is not a noble gas. Can that fluorine take any more electrons? It cannot, right? Because maximum of 8 there, right? Which is a big number there in bonding. So that's not good. That's not going to help calcium get to a noble gas configuration. So in this case, because of that, we need not 1 fluorine, but we actually need 2 fluorines in this case. Also has the same electron configuration. And now that will give our calcium somewhere to ditch his 2nd electron to, another fluorine, right? And what this will result in is calcium will now have our +2 charge. We will end up with a fluorine that has gained 1 electron, which means it will have a -1 charge. And we also ended up with a 2nd fluorine that also gained 1 electron, which will have a -1 charge. And what does that do for each of these things? Well, once again, calcium was able to get rid of both of its valence electrons in this case, 1 to each fluorine, which once again moves calcium back to 18 electrons and the same electron configuration as argon. So that makes calcium happy in this case. Each of the fluorines able to pick up 1 electron right there. And when they pick up 1 electron, that makes the fluorine here with a -1 charge be 1s2, 2s2, 2p6, which is 10 electrons, which means each of these fluorines here now have the same electron configuration as neon. So in this case, we actually needed 2 of the fluorines to allow calcium to lose enough electrons. I think we talked about it the other day at the end of chapter 4. What do we do when we take something with a +2 charge and a -1 charge? When we take something with charges and we want to write a chemical formula, the overall charge needs to equal what? Overall charge needs to equal 0, if you remember, right? So when we put them together, we want to get it to 0 with the simplest possible. The real reason we do that with ions is this reason. It allows everybody there to reach the noble gas configuration and be stable. And that is why we need not 1 of these guys, right? We need both of those guys to give us our proper formula of CaF2. So there is a reason why we talk about when we put ions together in terms of its formula for the compound, why we want it to equal 0. And the simplest way to get it to equal 0 means that everybody there has transferred and accepted the right amount of electrons to reach noble gas configuration. So it actually has to do with the bonding aspect of it as to why we put it together, and it has a zero charge. Any questions on that there? Questions on ionic bonding. So when you draw ionic bonding, you do need to make sure that you do show the charges. You need to show the kind of electrons where they're heading and ending up. And any questions on how to do that? All right, then let's talk about the other type of bonding, which is covalent bonding. And covalent bonding is, once again, between two nonmetals. And as I talked about earlier, they both have pretty much the same sort of periodic trends, which means they really do want to hang on to their electrons. So this is the situation when we get these guys together, which are all upper right of that staircase on the periodic table. When they come together, they're going to just basically agree upon sharing electrons. So we'll have some sharing of electrons happening here. And as we will talk about, once again, the sharing may be equal or maybe unequal sharing electrons, but there is some aspect of sharing that's always happening when you have a covalent bond that's happening. So our guy, Gilbert Lewis, suggested the role of electrons in chemical bond formation, hence Lewis structures, Lewis dot symbols. So when we take two hydrogens like we see here, they each have one electron. Because they're both hydrogen, they pretty much have the identical periodic trends because they're the same element pretty much, which means they both are not going to want to give away their electrons. So what's going to happen is, in this case, these two electrons are going to be shared between the two instead of being transferred. And what happens is we will get a covalent bond that will form between the two hydrogens, where we can show it as two dots. We could also show this bond here as a line. One line represents basically two dots are a single bond. And why is this important? Well, if we look at the hydrogens here, those two electrons that are being shared will count for the hydrogen there on the left, which means it has two electrons through sharing electrons here. And the two electrons in the middle will also count for the hydrogen on the right, which means it also has two electrons through sharing. And that's really important for what we talked about earlier today. When we look at the location of hydrogen and the noble gases we talked about that comes right after hydrogen is helium. And again, helium has two electrons, and that is why hydrogen should only have two electrons. It just needs to get to helium to be stable. So don't put anything more than that in this particular case. Now, in terms of that, as we will see, there's also double bonds, which are four electrons or two pairs of electrons. Could be represented either way. And we'll also see a little later, there's a slide, I think, as well. Triple bonds, which are three lines, and that represents six total electrons or three pairs of electrons, which is a triple bond. You could show these type of electrons that are making these covalent bonds as these dots are lines. I personally use lines most of the time to represent the type of bonding, but if you want to use dots, you can. But either way, they do count for both guys in the bond. This is a covalent bond, and what's really holding that together is, if you kind of think about it, right, there's like the nucleus kind of in the middle there of both of those guys. So there's the attraction of those electrons that are being shared to the nucleus of one, and also the attraction to the nucleus of the other. So it kind of locks them in place between the two, and that's what sort of holds those guys together in terms of those bonds. And that obviously is a covalent bond, which occurs between two nonmetals always. So this is how you could quickly identify if you're dealing with ionic or covalent bonding, is what type of elements are involved. So if you see a metal and a nonmetal, ionic, you're going to have a transfer of electrons. If you see two nonmetals involved, always going to be some type of sharing of electrons going to happen, and a covalent bond that's going to happen. So again, that's quickly how you could sort of identify the different types. So let's take a look at an example. If we look at something like fluorine, and we write the electron configuration for fluorine like we did previously, these is the 7 valence electrons that fluorine has. So we would have basically our 2 fluorines here. And once again, they are going to end up sharing these electrons rather than transferring them because they both want to hang on to them. And we will end up with something that looks like this. And again, if you use all dots, it will look something like this. And if we count up our electrons here with those guys in the middle, the fluorine there on the left now has 2, 4, 6, and 8 electrons. And if we count the fluorine on the right there, which would also include those 2 in the middle that are being shared, 2, 4, 6, and 8 electrons. Yeah. 8 is a magical number in bonding because group number 8 on the periodic table is the noble gases, right? Which is, as we've been talking about, pretty much the purpose of bonding, right? So in this case, both fluorines are able to achieve that sort of noble gas configuration in terms of their electrons by sharing those electrons between them. You can draw it like on the left there, all dots, or you could show the electrons that are being shared with the line, which again is most of the time how people draw it, but neither one is incorrect. So you could do it either way. And again, that one line represents 2 electrons, right? So that one line represents 2 dots that are being shared in this case. When we look at these electrons in this picture, there are a couple of different types of electrons that we talk about, especially in bonding. All these electrons, which are dots, and should be included in your pictures, they are not involved in bonding. And I know they're not involved in bonding because there's no other element on the other side there, right? So they're just dots and nothing on the other side of it, basically. And these are what are referred to as non-bonding electrons. Or if you're old like me, and I probably will say it a lot of times, a lot of books don't use it too much anymore, but lone pairs are the same thing as non-bonding electrons. So I probably will say lone pairs, but most books nowadays will use non-bonding electrons. They mean the same thing. They're basically electrons that are not involved in any type of bonding. Now, that is different than obviously the electrons we have in the middle there that we've talked about, which are involved there in bonding. So these electrons here in the middle, which are involved in bonding, also has a very creative name. These are known as bonding electrons. Yeah, so that makes sense, I suppose. So electrons involved in bonds are referred to as bonding electrons. Non-bonding electrons or lone pairs are really represented in Lewis structures as dots. And I would say most of the time that is how they're sort of represented when you draw them. Most of the time the bonding electrons are shown with lines and the non-bonding electrons are shown as dots. But once again, you can still use dots for the bonding electrons if you want to. It's okay. But you do need to show all those electrons when you draw Lewis structures, not just the bonding electrons. So you got to show all the electrons that are involved. So a Lewis structure is a representation of covalent bonding where we use, again, Lewis dot symbols to show bonding through lines or dots. Once again, a reminder that all these elements do have other electrons, which are their core electrons, but once again, they are not represented in Lewis structures. Just those valence electrons are represented. So if we look at water and we draw a Lewis structure for water, it will look something like this, H2O. And in the case of water here, let's draw it all as dots. There's a lot of sharing going on here, but the sharing is going to help everybody basically get to that noble gas configuration, if you will. Here, the hydrogen sharing some electrons with the oxygens allows hydrogen to get to 2 electrons, which is exactly what it needs. The hydrogen on the other side, also through sharing electrons with the oxygen, will allow it to get to 2 electrons and really neon's configuration and be happy. And the oxygen, by sharing electrons with both of the hydrogens, will achieve 8 electrons, which also allows it to reach that noble gas configuration. So in this case, a lot of sharing going on, but the end result's the same. Everybody ends up same sort of electron configuration as those really stable noble gases, and really the point of all of the bonding that's happening here. We will later on talk about how to properly draw these and the steps to draw these structures a little bit later on in this chapter. Any questions on that there? So obviously we've been talking about this rule, but let's officially talk about the rule. And the rule that really sort of governs bonding is what is referred to as the octet rule. And in this class, we will obey the octet rule. We will talk about some exceptions to the octet rule, which we will not do in this class usually. When you go to 1A, you'll do nothing but exceptions to the octet rule, but here we will try to keep everything to obey the octet rule. And the octet rule basically means that everybody except for hydrogen will continue to make bonds until it has 8 valence electrons around it. So that is the goal, to continue to make bonds with other elements until you hit the magic number of 8, which should put you in the same sort of position as the noble gases. The one exception of that obviously is hydrogen. And once again, hydrogen should only have 2 electrons. That is what is sometimes referred to as the duet rule, that it should only have 2. Frankly, when you're drawing Lewis structures that have hydrogen, this is exactly what it should look like, just like that. And it should always be on the outside, because if you put hydrogen on the inside, it will have way too many bonds. Yes, way too many electrons. So hydrogen should always be on the outside, should never have dots around it, should pretty much look like that. If you use lines, if you use dots, you should only have something that looks like this. You should never have anything like this, which is super common. People just like, I remembered somewhere, like I got to fill up everybody with dots, so I'm just going to fill up hydrogen as well. Why not? And just for good measure, hey, let's throw a few extra bonds on there as well. You're just going to get one of those. Yeah. So don't do that. It should look like one of these 2 things always when you have hydrogen. So don't do any of the other things. So it's really important, and very, very common mistake that people make when they start drawing real Lewis structures. Yeah. Diatomic molecules just simply means that there are 2 atoms present. That's it. It could be 2 of the same element, it could be 2 of the different ones, but there's just 2. An atom is the simplest representation of an element. In order to be a molecule, you need at least 2 atoms present, 2 or more. Yeah. Yeah, it's just like if you had an atom of iron, right? You would just have the proper number of protons and electrons that go with iron, yeah, and it would just be 1, right? If you had, or just hydrogen, right? You had something like that, you would just have 1 hydrogen atom. If you put it together with another hydrogen atom, these guys will come together and make a bond. And now you have what is known as a diatomic molecule, which are those 2 together. But really the definition of diatomic molecules, and sometimes people think it always has to be the same elements coming together, and it doesn't. So it really is what the name sounds like. Diatomic just means that there's 2 atoms involved. So for example, something like CO is a diatomic molecule because it has 1 carbon atom and 1 oxygen atom. Yeah. Other questions? All right, so we touched upon multiple bonds. Let's officially look at it here. So really this comes about in terms of bonding, and the way you should think about it is this. In certain cases, in order for everybody to achieve the octet rule and to be really happy in terms of their bonding, sometimes all it takes is a single bond to do that. So all you might need to be making are single bonds. Now, sometimes it takes double bonds to get somebody to a sort of noble gas configuration. And once again, a single bond can be represented with 1 line or 2 dots. In the case of CO2 here, it takes 2 double bonds actually to get each of these oxygens to 8 electrons, and the carbon also to 8 electrons in this case through 2 double bonds. And that would represent again 4 total electrons or 2 pairs of electrons. So in the case of carbon dioxide, it needs actually like something like this. It needs those double bonds on each side in this case to give the oxygen on the left 2, 4, 6, 8 electrons. Oxygen on the right, 2, 4, 6, 8 electrons, as each line counts for 2. And for the carbon in the middle, it needs 2, 4, 6, 8 electrons. So sometimes it does require going to a double bond sort of situation. Maybe not on both sides like we see here in CO2, but you might need to lay up a double bond to get somebody to those 8 electrons as necessary. And sometimes it does require maybe a triple bond to get somebody to meet the octet rule. And a triple bond is something that has 3 lines. So here's a couple examples like nitrogen, for example. Sometimes you'll need a triple bond, which is 3 lines are 6 total electrons or 3 pairs of electrons. So in the case of nitrogen, do something like this here. It's kind of represent like that. When we look at the nitrogen on the right, by sharing all 6 of those electrons with the nitrogen on the left, it now has 8 electrons if you count up all the dots. And nitrogen on the left there, by sharing with the nitrogen on the right there, now has 8 electrons as well. And again, it requires a triple bond to occur in this case for that to happen. This also happens down on the bottom there. The carbons, by sharing with the hydrogen and also making triple bonds there with themselves, allows each of the carbons to get to 8. It also, as you can see here, still only allows, and what is necessary, the hydrogens to get to 2, right? They both have 2 electrons, which makes everybody happy. So a cautionary note of a common mistake that people make when they start drawing real Lewis structures, like we'll talk about in this chapter, is they want to always like triple bond and double bond right out of the box. Just start throwing lines down and bonds. And the good rule of thumb is you probably shouldn't do that. You should always start with kind of like single bonds. And then if you see something or somebody hasn't met the octet rule, then you want to try to fix it by making a double bond. If that doesn't work, you want to fix it by making a triple bond. So good thing to keep in mind is you should not go where a lot of people try to do, which is I'm just going to start throwing bonds on everything right out of the box. So like I said, we will talk about sort of the order and the steps to drawing these things a little bit later on in this chapter, but that's something to keep in mind for sure as we go through it. So what is sort of the property that helps us determine in terms of really covalent bonding, how these electrons are going to be shared? And that is a really electronegativity. And as we will see, electronegativity is the ability of an atom to attract electrons towards itself. And on the periodic table, as we will see in a few slides down the road, it increases as you go up and to the right and decreases as you go down. Actually, our friend fluorine is the most electronegative element you could have. It is the most electronegative and the guy that wants the electrons the most. And that is because if you look at the periodic table, now there's nobody really past fluorine, if you will, upper right, except for noble gases, right? And noble gases are chemically inert, which means they're not looking to do much. They actually have no electronegativity. They have a 0 value actually, because they're pretty much happy the way they are. So that's why we kind of stop at fluorine on the periodic table, because to the right of them are the noble gases, which aren't looking to really do much in terms of bonding and stuff like that. So electronegativity helps us determine how the electrons are going to be shared between 2 atoms within a bond. And for example, if we take our hydrogen atoms that we talked about and we make our bond like we did, we would probably expect that the hydrogen atoms would both be pulling on those electrons pretty equally, right? Because they're both the same element, pretty much like a tug of war, if you will, right? So you've got 2 people on opposite sides of a rope and they're equal in strength. Really, the rope isn't going to go anywhere, right? As they pull, right? They're going to kind of cancel each other out. And because of that, we would expect, in terms of the electrons, to be shared equally. So we would expect equal sharing of electrons. And when we have a covalent bond that has equal sharing of electrons, that is what is sometimes referred to as a nonpolar covalent bond. Or most people drop the covalent part of it and just call it a nonpolar bond. It's sort of implied if you see nonpolar that you're talking about covalent bonding. So sometimes people kind of drop that out. So in a nonpolar covalent bond, we have basically equal sharing of electrons. As we will talk about, there is some degree of what we consider equal sharing of electrons. But if we have perfectly equal sharing of electrons, which would be the case in this case, they're both the same element, that is also sometimes referred to as a pure covalent bond. So a pure covalent bond is really still a nonpolar bond, but that's like perfect equal sharing of electrons between the two atoms. So what does this mean? It means that this bond is nonpolar and essentially neutral in a sense. We have nice equal distribution of the electrons over the bond. There's no side that's more positive. There's no side that's more negative. It's kind of like a neutral bond, if you will. There's really nice, perfect equal sharing of everything that's happening here. Now, what happens if we swap out the hydrogen for something like fluorine here? Now, between hydrogen and fluorine, as I just mentioned before, there actually is a difference in electronegativity. And between hydrogen and fluorine, which one is more electronegative? It is fluorine. What that means is, in terms of electrons, it is the fluorine that's going to go, I think I would like the electrons more than you, basically. So what's going to happen as a result of that is, if this yellow is like the electrons, we're just going to get a big buildup of electrons over here on the fluorine side, and not so much happening there on the hydrogen side in this particular case. This is also like the tug of war example. You got somebody on one side of the rope, right? Much stronger than somebody else on the other side. The guy's going to hold on for dear life, right? And he's going to start moving and stuff like that. So what happens is we're going to get more of the electrons hanging out towards the fluorine than the hydrogen side of this bond. And that means that we're going to get unequal sharing of electrons that's going to happen here. And because of that, and the fact that the fluorine here will now have more of the electrons hanging out over there versus the hydrogen, would we expect the fluorine to be more positive or more negative in this case? If they have more of the electrons, they should be negative, right? Electrons are negative. So what that's going to create is a partially negative charge on the fluorine. That's a delta symbol, so delta negative. And that means that the hydrogen, which has less electrons hanging out over there, will become partially positively charged in this case. This also could be represented with an arrow, which you will commonly see in bonding. And this arrow looks something like this. This is what is sometimes referred to as a bond dipole arrow. And the arrow always points to the more negative side. And the back part of it, which kind of makes like a plus sign, is the more positive side, is where it sort of is. And that is also sometimes representative to it. So this type of bonding where we get unequal sharing of electrons is what's known as a polar covalent bond, or just a polar bond. Again, a lot of people take the covalent out of it. So the question I have is, why is it a partially negative charge and a partially positive charge rather than a full positive and full negative charge? Why is it only partially positive and partially negative? Yeah. Yeah, there's still some aspect of sharing that's happening here, right? So kind of like my example with the rope, that poor guy that's a lot weaker, right? He's going to hang on for dear life, right? So, but he's still hanging on, right? As he gets dragged around the mud, right? And stuff like that. So there is still some aspect of sharing that's happening here. We do not have any transfer of these electrons. So there is still sharing that's happening here. Definitely unequal sharing in this case, really unequal sharing in this case. But there's still that aspect of sharing. That's why we get partially positive and partially negative charges rather than like we see in ionic bonding where there is no sharing of electron. The electron is fully transferred. So we get those full charges that result with the metal and the non-metal in that case. Any questions on that there? So as I mentioned before, this is what happens in this case with HF, and again referred to as a polar covalent bond or just a polar bond. And unlike a non-polar bond where you can kind of think of it as being neutral, in a polar bond we have this sort of charge that occurs. There's a positive side and a negative side. And that happens, as we will talk about in other chapters as well, that has a great effect on things like solubility, how other molecules maybe behave with other molecules, the presence of these type of charges, and it does play a pretty big effect in a lot of areas. And again, we can represent that type of bonding with that arrow. Once again, it points to the side that's more negative, and once again, the back end there to the side that's more positive. And that's usually sometimes how we represent bond polarity. That's what it's sometimes referred to.
So can you
Yeah.
real quick explain analogy again with the pulling the thing on?
Yeah. So if we think about a non-polar bond like the two hydrogens, you can think of like tug of war. Yeah, everybody's familiar. Rope, right? Flag in the middle, right? Mud in the middle, everybody. Right. So in a non-polar bond, you got basically two guys on the opposite sides of the rope that are pulling equally, right? Which means the rope and nobody's going anywhere, right? Kind of like on a door, right? You're pushing equally on one side versus the other, not going to go anywhere. So that's basically going to result in equal sharing of electrons. There's not going to be a side that's more positive or more negative because those electrons are basically going to be stuck there in the middle, nicely equally sort of spread out over, makes a non-polar bond. In a polar bond, what you have in terms of that analogy is you have one guy on one side of the rope that's much stronger than the other guy. And if you think about the rope or the flag, if you will, in the middle, as the electrons, that one guy's going to be able to pull the rope much stronger. That guy's going to be more negative because he's bringing those electrons towards himself. And it's going to create this definitely separation of charge that's basically going to happen. He's going to be able to kind of drag all the electrons to itself. But what I was saying is that poor guy that's weaker is still hanging on, right? So they're still sharing technically the rope, even though definitely unequally as he gets dragged through the mud, right? Because that guy's pulling pretty strongly and stuff like that. Yeah.
The chlorine, that example of the guy that's still pulling on the rope.
Yeah.
Still has a little bit of negative charge, but his sign is, or he still has electrons, right? So the sign is positive. Is it positive because it's like
The hydrogen is more positive in this case because the electrons are basically, if you want to think about it, vacationing on this side of the bond. And it's basically all those negative guys are hanging out over there, most of them. And that's going to just get a buildup of negative charge on that side. And that's why it's partially negative. The result of that is the hydrogen is seeing a lot of its electrons going on vacation away from him, right? And that's going to make him kind of like electron deficient and more positively charged in that case. Yeah. Other questions? All right. So to summarize the different types of bonding we talked about up until this point, you could think of on one end of the extreme, we have ionic bonding. And that is always between a metal and a non-metal. And again, as we talked about, we will always have in this case the metal transferring some electrons over to the non-metal. The result of this is we will have a cation, which is positively charged, attracted to an anion, which is negatively charged. It is that electrostatic attraction. And that is, an example, say like sodium chloride. Sodium's a metal, chlorine's a non-metal. Sodium's going to lay up its electron over to the chlorine. Sodium will become positively one charge. Chlorine will become negatively one charge. And again, no sharing of electrons happening here. On the other end of the extreme, you have a nonpolar covalent bond. And that is between two nonmetals. That is covalent. And that means that we have equal sharing of electrons. And an example like that is something like our F2 that we saw, our H2, and so forth. Equal sharing of electrons, no side that's more positive, no side is more negative. Nice, everybody's happy, nicely equally shared there. And in the middle of those two, we have a polar covalent bond, which is also between two nonmetals, also covalent, and we have unequal sharing of electrons. The result of that is something like HF, where the fluorine is more negative because it has that more electronegative, is going to drag the electrons towards it. The hydrogen is more positive, and we get this unequal sharing of electrons as well. So at one end of the extreme, ionic, no sharing, just complete transfer. Other end of the extreme, perfect, nice, equal sharing of electrons. In the middle, we have unequal sharing of electrons, not unequal enough that the electrons actually transfer, but they still hang on and they're still sharing, but definitely unequal, causing the kind of separation of charge that occurs. Any questions on any of that there? So what helps us really determine sort of in a covalent bond really what's going to be sort of a polar bond or a non-polar bond. You could also use electronegativity to help you determine ionic bonding, but you really don't need it because all you need to know is metal, non-metal, ionic. You really don't have to worry about it. So really electronegativity a lot of times is used as really the determining factor of will these two elements come together and make a polar bond? Will they come together and make a non-polar bond? And electronegativity, again, is the ability of an atom to bring electrons towards itself. And it's based on two other periodic properties, which we'll talk about a little bit later on, I think today, maybe in lab, electron affinity and ionization energy. Electron affinity is the energy change that occurs when atoms gain electrons, so kind of like an anion situation. And affinity, if you just think about it right, is basically somebody likes something, has an affinity for it, so they have an affinity for electrons. Ionization energy, as we'll talk about, is basically the energy required to remove an electron. So that's what cations. So basically, those trends tell us what we talked about, that as you go up and to the right on the periodic table, electronegativity increases. As you go left and down on the periodic table, it decreases. And I think it's probably a good place to stop, actually. So we will lay it up there.